typical notice of copyright. After viewing these videos on calculations required by CSEC Physics Syllabus 2015, I hope that you are a little more comfortable with using these formulae. They are required on the CSEC 2015 syllabus, which normally runs for 10 years, after which they are revised and updated. However, in terms of formulae, a revised syllabus will not have much change, if any, since these formulae are mainly based on classical or what we call Newtonian physics. Formulae you are required to know for CSEC Physics Examination 2015 syllabus. There are some basic principles that we need to learn or keep in mind for all of these 35 or so formulae for the CSEC Physics Examination. First, you need to actually remember the formula themselves, including the variables, uppercase or lowercase letters. That's the first thing. Secondly, you need to remember what the symbols represent and the required units allowed in that formula. Third, if required, then you need to change the subject of the formula. Fourth, substitute the values you are given and solve. And 5, check that you have the correct number of significant figures and also you have the correct unit for the answer. And if possible, 6th, subjectively evaluate your answer by asking yourself, is my answer reasonable? For example, if you have to find the effective resistance of 3 resistors in parallel and they are 25 ohms, 55 ohms, and 12 ohms, if you do that and you get an answer greater or equal to 12 ohms, you know that that answer is wrong, since the answer to this question must be less than the least of the resistors. So it must be less than 12 ohms. Anything equal to or greater than 12 ohms would be wrong. So these are the formulae we looked at. For mechanics, we covered all of these, and we will meet this again in atomic physics. For thermal physics, we dealt with all of these formulae and their variations. For waves, sound and light, we looked at those. For electricity and magnetism, we considered these 7, including this one, which is a combination of formulae 2 and 3. And then for atomic physics, we looked at these. Recall again, E is equal to mc squared. Talked about half-life and half-life from decay curve or decay graph. Now, those are all the formulae that you are required to know for CSEC Physics Examination as stipulated by its 2015 syllabus. Now, there are about 4 other formulae that you are not required to know, but they will help you to better understand some of the other concepts that you are required to know about. And I may deal with those in video Physics 25, May, after I get through with the next 3 videos on graphs, including this one. So 22, 23, and 24 on graphs. And then I may consider looking at those other 4 formulae that you will find useful. Now, graphs are an integral part of physics, extremely important. In this video, that is Physics 22, I will deal with drawing a typical speed time graph and distance time graph, and then learn how to use such graphs. Well, that was the original intention, to deal with both speed time and distance time graph in this one video. But this video will then be too long, so I will split it in two. Physics 22 Part A, dealing with the speed time graph, and Physics 22 Part B, dealing with the distance time graph. Now for the speed time graph. We will just look at one example in detail. A car accelerates from rest to 9 meters per second in 10 seconds. It retains this speed for 15 seconds. The car then accelerates to 24 meters per second in 30 seconds. It retains this new speed for 1 minute and 15 seconds. The brakes were then applied and the car came to rest in 8 seconds. First thing you are required to do is draw a speed time graph to clearly show the journey of the car, and you will assume uniform acceleration. I will explain what that means. Now, after you get the graph, you will use it to do certain things. Find the total distance traveled by the car, find the average speed of the car for the whole journey, find the acceleration of the car during the third part of the journey, and find the acceleration of the car during the last part of the journey. In the actual exam, CSEC exam, you will be given a blank black and white graph paper with directives of what variable to place on which axis, but you will not be told about the scale. You will have to determine that for yourself. I am stressing blank, black, and white graph paper in the actual exam for a reason. And I'll explain that in a little while. So let us say our paper looks like this. Well, firstly, we have to determine how many quadrants we will need. So if you draw, normally when you do math, you will draw an axis coming straight down like this in the middle there, and another one going across like that. Now this one over here is called the first quadrant. This one over here is called the second quadrant, quarter. This one over here is called the third quadrant, and this one over here is called the fourth quadrant. And later on, we'll look at a possible scenario where you have to use all 4 quadrants in math class. But in physics class, most likely, all you have to do is use this first quadrant here. Now, since all values are positive, we will only need the first quadrant. That's this one over here. Now, using a black pencil to draw the axis will not show when you scan this paper or when the paper is scanned. If it's an actual exam, CXC exam, the papers are scanned, computerized, digitized, so that markers could mark them electronically. So make sure that you use some kind of system, maybe a dark blue or black pen, and bold this line here and that one there, the axes, such that they can be easily differentiated from the other bold line, like that one there and that one there. So we'll draw 2 axes to indicate the first quadrant only, which would be these 2 axes here. Notice you can clearly identify them. And as I said, use a dark blue or black pen so that the axes are thick enough or bold enough that they are clearly differentiated from the other bold lines. In the examples that I will be doing, I will use a graph paper that has blue lines, so you can clearly see the work that I am doing and how to do it.
So here we have a graph paper. Normally in math class, if we have to draw a graph, we will draw a y-axis like that, and then an x-axis somewhere here depending on the values that we have to use. And most times we will use all four of these quadrants. So this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So you may have to get a graph that looks something like this. So that you have a curve here, you have a straight line here, and then you read off this point and this point, or you take this area here that's in your math class. Now for physics, most of the time, all we have to use is this first quadrant here. So here is 2022 physics CSEC exam. And as you can see, they already drew in the two axes for you, the x-axis and your y-axis. So this is just the first quadrant. CXC paper 2, 2023, same setup. The y-axis and the x-axis, and all we're using is the first quadrant. And by the way, in this 2022 paper, you have to plot A versus time. So over here would be A, whatever that is, and over here would be time. In this case, you're plotting temperature versus time. So down here will be time, and over here will be temperature. And then CXC, CSEC 2024, that is this year. Notice the two axes are already drawn in, and this time you are to plot magnification over here against image distance. That is, you plot magnification over here M, and on this axis it would be image distance V. That is for CSEC examination. In our case, we have to plot a graph. It's a speed time graph. Example 1, a car accelerates from rest to 9.0 meters per second in 10.0 seconds. It retains this speed for 15 seconds. It then accelerates to 24 meters per second in 30.0 seconds. It retains this speed for 1 minute 15 seconds. The brakes were then applied and the car came to rest in 8 seconds. First of all, we have to draw a speed time graph to show this journey. As I just pointed out, in this case, this speed time graph will only require quadrant 1. So we bold this line down here. This will be our x-axis. And then we bold this line here. So this is our x-axis. This one here is our y-axis. Normally on a speed time graph, this x-axis here, which is the independent variable, is the time. And in this case, it is seconds. And this axis here is the speed in meters per second. So you must draw your axes, you must label them. Now, the next thing is probably the hardest. We have to scale out these two axes. So since this is time, we will add up all the time here. There is 10 seconds here, 15 seconds here, 30 seconds here, 1 minute 15 seconds, which would be 75 seconds, and then 8 seconds. Now, if you add all of that together, you will get 138 seconds. So we need to fit 138 seconds here. Two things we need to bear in mind. We must use at least half of this axis. And secondly, we must choose such a scale that we can easily read the sensitivity on this axis. So if we want to fit 138, we can start with and begin with 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. That's not going to work. So let's go with 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 138. That will work. So let's scale it out. This is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. We could put a 140 here. 140. Remember, we're going to 138. We could even put in a 150 here, though of course we wouldn't need that 150. So now we have the scale here, so we could write in on this axis, scale 1 centimeter, that is 1 centimeter, is equal to 10 seconds. So a centimeter is about the diameter of your pen. Centimeter is about the diameter of your pen. And you don't have to measure it with a ruler. These bold line here, from here to here, is 1 centimeter. Now, you also need to know what your sensitivity is. Sensitivity is the smallest difference you can measure here. So if from here to here is 10, and you have 5 little divisions, then 10 divided by 5 would give you 2 seconds. So if this is 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and so on. Now, so that's your scale. 1 centimeter is 10 seconds, and on the x-axis, and the sensitivity is 2 seconds. Now, on this axis, you don't have to add up all the speed. You take the highest speed. So what is our highest speed? We have 9 meters per second. We have 24, so it's 24 meters per second. So we need to fit 24 meters per second here. Now you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. That's pushing it a little. So let's, instead of doing that, let's go to 2. So you put a little line here exactly across that, put 2 here, exactly across there, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's how far we want to go. But we could just put in here a 26 and a 28, though we wouldn't use it. And of course, we write in the scale. Over here, the scale is 1 centimeter is equal to 2 meters per second, and the sensitivity is, if from here to here is 2, and you have 1, 2, 3, 5 divisions, then 2 divided by 5 would give you 0.4 meters per second. Okay, now that we have that, we will begin to plot the points. First thing is the car accelerates from rest. So our force point is here at 0 time, the car is at rest. It then accelerates to 9 meters per second in 10 seconds. So 10 seconds is here, and we are going up to 9, that is 8, that is 10, 9 would be exactly halfway between here. So you come across here and you put a little dot here with a little O around it. And that will be the force point we need. We will draw a line from 0, 0 to 10, 8. Like that, and that represents the first part of the journey. Now it says that it retains this speed for 15 seconds. So 10 and 15 more will give us 25. Now be very careful here. Remember we said the sensitivity on this axis is 2. So if that is 20, 22, 24, 26, 25 will be halfway between here. So we estimate 25 here, come up here, and we are at this point. So we go up at 25, we come across at 9 because the speed didn't change, and we draw a line from here to there, and that represents the second part of the journey. It then accelerates to 24 meters per second, so it goes right up to 24, which is this point here, 24, in 30 seconds more. So if we were 25, 30 will take us to 55. So 50, 60, 55 is here. You can use your ruler to trace, to make a little line here in case you feel you'll get lost, because it's easy to get lost with these lines. We are going up to 24, which is here. You may even use some broken lines like this, some dashed line like this, but those are not really required. So we reach here 24 at 55, and we draw a line from here to there. This represents the third part of our journey. It says that it retains this speed, this same 24 speed, it retains it for 1 minute 15 seconds. 1 minute 15 seconds. So we were at 55, we now add 75, 5 and 5, 10, 8 and 5, 13. So we are going to end up at 130 seconds, that is here. So we go follow this line here, 130, follow that 24 there, and we arrive at this point. Again, you could draw little dashed lines like that here, or wherever you like, to make sure you don't lose your space. Finally, it says the brakes were then applied and the car came to rest, which means that the speed come down back to 0 in 8 seconds. So we're at 30, 32, 34, 36, 38. That is this point here. And so We draw a line coming down from there to here. And that is the required graph. So what we have done, we have taken this word problem and put it in a graph format. So if we didn't have that word problem, we know that something. Now when you have a slanted line like this on a speed time graph, it means acceleration, going up from your left to your right. If it goes down as you go from your left to your right, that's deceleration. Any line going straight across means the same speed. So we can if we didn't have that, we can read this. Some kind of object accelerates from 0 meters per second to 9 meters per second in 10 seconds. It retained that speed for 15 seconds. That's 10 and 15, 25. It then accelerates to 24 meters per second from 25 to 55 would be 30 seconds. It retains that speed for 1 minute, 15 seconds, or 75 seconds from here to there. And then it came to a stop in 8 seconds. So that's the graph that we had to draw. Second part of the question says that we are to use this graph. Now, the question says we are to use the graph, first of all, to calculate the total distance traveled by the car. That's the first thing we have to do. So we have the graph. Now to do that, there is something called the area under the curve, or the area under the graph. So if you look carefully, I'm going to draw a line coming down here, a thin line. Let me draw it bright so you could see it. You will notice we have a triangular shape here. Let's call that A. Now, if we find the area of this triangle, we would have found the distance the car traveled as it accelerated to 9 meters per second in 10 seconds. In a similar way, if we find the area in this rectangle here, and we will call this B. As you could see, we have a rectangle. The rectangle is 9 meters per second going up that way and 15 seconds this way. Over here, we have a shape. I hope you can remember what that shape is. It's a trapezium. We will call this C. And over here, we have a rectangle, a fairly large rectangle. Which we will call D. And we have a small triangle here, which we will call E. Now to find the total distance traveled, we will calculate the area under each part of this graph and add them. Now, don't let the word area deceive you. We are not going to get square units, and I will explain that in a little while. Now, this shape here, A, is a triangle. Its area will be half of the base times the perpendicular height. So it will be half of 10 times 9. Half of 10 times 9. But notice this 10 is seconds and this 9 is meters per second. So that this second here will cancel out that second there and you will remain with meters. So for A, we get the area is equal to 45 meters, not square meters, 45 meters. For B, which is a rectangle, we have 15 seconds times 9 meters per second, and we get 135 meters. That is the distance the car would have traveled from here to there. Then for C, which is a trapezium, and if you recall how to find the area of a trapezium, you find the sum of the parallel sides, divide by 2, or another way to state that is find half of the sum of the parallel sides and then multiply it by the distance separating those parallel sides. So this side here is 9, that side there is 24. If we add them and divide by 2, and then multiply by 30, we will get 495 meters. So during this part of the journey, the car traveled 495 meters. Now D is a rectangle, as you could see. This way, this dimension here is 24 meters per second, and this way is 75 seconds. You multiply those two and you get 1800 meters. And finally, we have this thin triangle here, half of the base, which is 8 seconds, times the perpendicular height, which is 24, and this area here is 96 meters. Now, I am saying area because that's what you would normally do to find the area of these shapes. However, the answer is not square units, it is meters. If you add all of these, you get 2,591 meters, and we need to round that off to two significant figures, and so we get 2,600 plus or minus 50 meters. So that's one part of the question. Next part of the question says, find the average speed of the car for the whole journey. Okay, well, this is not very difficult. You just found the total distance here. Average speed is equal to total distance divided by total time. We found the total distance, and we will use this value here, not the rounded off value. Divide by the total time, which we already calculated as 138. We divide those two, and we get 18.63 meters per second. And we average that off to three significant figures, which is 18.6. The third part of the question says, calculate the acceleration of the car during the third part of the journey. So this is the first part, this is the third part. So we want to find this acceleration. Now recall, anytime you have a speed time graph and you have a slanted line like this from the left to the right, it is acceleration. Now if it's slanting downwards, it is deceleration. So we want to find the acceleration here. On a speed time graph, the acceleration is actually the gradient. The acceleration is the gradient. So we are going to have to find the gradient. As you know, gradient is increase in y divided by increase in x. So what we will do, we'll draw a line across here. Make a square here. So we have a triangle here, a right triangle. To find the gradient of this, we'll have to find the increase in y. Now y starts here at 9 and it ends at 24. That's y. X starts here at 25 and it ends here at 55. So increase in y, we started at 9 and we ended up at 24, would be 24 minus 9. And that, of course, is meters per second. And increase in x, we started at 25 and we ended up at 55. So it would be 55 minus 25, and that would be seconds. When you work this out, you get 15 meters per second divided by 30 seconds, which will give us, that's not 0.05, that would be 0.5. 0.5. So we get 0.5 meters per second, which gives us 0.5 meters per second squared. So that is the third part of the question. Using the graph, we calculated the acceleration of the car during the third part of the journey. Now, it also says, using that same graph, to calculate the acceleration of the car during the last part of the journey. Okay, well, we already said that acceleration is the gradient. So let's see. So we want to find the gradient of this. So we want to find the gradient. Acceleration is equal to increase in y, note what I'm saying, increase in y, divided by increase in x. Well, y started at 24 and ended up at 0. At 0. Why? This y, we started at 24 and we ended at 0. So what's the increase in y? It will be the final value minus the initial value, which would be 0 minus 24. As it relates to the x value, we start at 130 and we end at 138. So the increase in x will be 138 minus 130, and so we get minus 24 meters per second over 8 seconds, and that gives us a negative 3 meters per second, which is meters per second squared. Now, do not bother about this negative, because we are finding the acceleration, and this is actually deceleration. We got a negative acceleration. So the deceleration is actually 3 meters per second squared, but you were not asked to find the deceleration. You were asked to find the acceleration. And for acceleration, your answer is this, negative 3 meters per second squared. If they had actually to find the deceleration, you will still go ahead and find this, but then you will swap out this negative here for a positive here, which is just leave it blank. What did we do? We got the graph, and then we use the graph to find those things. Now, just to compare one or two things here. Let's say we want to find c, which is this distance here. We know that the initial speed is 9 meters per second. The final speed is 24. The time is 30 seconds. If we are going to calculate it using the equations of motion, we know v is equal to u plus at, v squared is equal to u squared plus 2as, and s is equal to ut plus half at squared. We learned about those in Physics 09 video. We want to find s. Now we can use this formula, but this formula requires an a, which we don't know. So we will use that formula up there to find the a, or substitute the a into here. So we know from Formula 1 that a is equal to v minus u over t. So we rewrite this equation, equation 3, and we replace the a with v minus u over t. We don't have to do this. We can factorize, take a t from there and take a t from there, so you get t into u plus half over v minus u over t, and then we can eliminate that t and that t. So you're left with s is equal to t times 9 plus half times 24 minus 9. If you work this piece out, you will get 7.5. You add that to that 9, you get 16.5. Multiply that by 30 and you get 495 meters, which is exactly what we got here. Notice, of course, this 16.5 here, which is, if you add 9 and 24 and divide by 2, you will get 16.5, and then you multiply by 30. So if you had to calculate it, that's just to double check that our work is correct. In this case, we find that it's much easier to find the distance here for part C using the graph than to do this calculation. You could have, of course, just calculated the A up here. A is equal to V minus U over T. A is equal to V minus U over T, and you get this 0.5 here. Take that 0.5 and now substitute it into this equation here. And so you get 9 times 30 plus half times 0.5. This half cancel that 30. This half cancel that 30. You get 15, 15. And so you're left with 270 plus 15 times 15, 225. And you get back 495. Now, in this case, it's kind of difficult to do the calculation using the equations of motion and much easier to use the graph. But notice also, you are to find the acceleration during the third part of the journey, the acceleration here. Using the graph, we had to find a gradient. But if we were just using calculation, in this case, calculation would be much easier because, as we said, the acceleration is V minus U over T, and we quickly get 0.5. That is using the equations of motion. However, in this case, you are asked to use the graph to do these things. And so we use that. So this is a speed time graph, and from the graph, you had to do certain things.
And that brings us to the end of Video Physics 22A, Speed Time Graph. Next, we will consider Distance Time Graph in Physics 22B.